Hello, my name is Aiden Moran, and welcome to my first Transport 1 video of the year. So the first topic that we're going to jump right into is concentric cylinders. So as you can see, we have a pair of concentric cylinders here. The large cylinder with a radius of big R will be stationary, and the inner cylinder with a radius of R sub I will be turned to some angular frequency omega. And when this is turned to some angular frequency, it will have a torque on it. But because this system as a whole doesn't move, we know that the outer cylinder has to also apply torque with an equal magnitude to the inner cylinder. So what we want to do is prove that to be true. We're going to derive an expression that shows that the torque on the outer cylinder is equal to the torque on the inner cylinder. So to do this, we were given a couple equations, one for the shear rate and one for the velocity at some given beta. So if we look at the top view of these cylinders here, you can see this point here at some distance r from the center as a velocity. And we want to relate it to angular frequency and eventually torque. So the first step in doing this is to find the shear rate at both the inner and the outer cylinder. So first we'll do the inner cylinder. And to do that, we need to combine these two equations. So the first step in doing that will be to divide this top equation by r. So that gives us d theta over r equals omega times k squared over 1 minus k squared. And then I'm going to distribute this divided by r into this term, which will give me r squared over little r squared minus 1. So from there, we want to take a derivative of both sides with respect to r. So we'll have d over dr, d theta over r is equal to, and you can see all of these do not have an r, so they will be the same. The derivative of r squared will be negative 2 r cubed times r squared and minus 0, because the derivative of 1 is 0. And then once we do this, all we have to do is multiply by r, and then the left side of our equation is equal to the shear rate. Let's do that. R d over dr d theta over r is equal to omega k squared over 1 minus k squared times negative 2 r squared over r squared. So now what we want to do is plug in the shear rate for the left side of this equation. So this will be the shear rate is equal to omega k squared over 1 minus k squared negative 2 r squared over r squared. So that'll be the equation that we'll use for our shear rate. So now that we've derived this general equation for shear rate at any given radius, we need to plug in the radius equal to the inner radius and solve for the shear rate at the inner radius. So let's call this shear rate r equals ri equals omega k squared over 1 minus k squared negative 2 r squared over r sub I squared. And if you remember, we have this term down here, k, which is a ratio of the inner radius to the outer radius. So a little bit of rearranging gives us the inner radius is equal to k times the outer radius. So we're going to sub that in for ri squared right there. And I'm also going to move this negative 2 out. So substituting that in gives us k squared times r squared. And as you can see, there's a lot of stuff that can cancel here. That k squared and that k squared cancels. And that r squared and that r squared cancels. So now we're left with the shear rate at the inner radius is equal to negative 2 omega over 1 minus k squared. And now we can do the same for the outer radius. So we'll take this equation here and sub in r is equal to big R. Now, as you can see from there, these r squareds can already cancel. And so this just leaves us with the shear rate at the outer radius is equal to negative 2 omega k squared all over 1 minus k squared. So now we've developed equations for the shear rate at the inner and outer radius. We can use that to find the torque at the inner and outer radius. So now that we have the shear stress at the inner and outer radius, the next step is to relate that to the torque at the inner and outer radius. So first, we need to define the shear stress. So the shear stress is going to be equal to the viscosity of the fluid times the shear rate. And we know the torque is equal to the force times the radius. And this shear rate can be used in the force and multiply it by area. And then a little bit of substitution will give us the torque is equal to mu times viscosity times the area times the radius. So now that we have this general form, we can plug in the shear rate at each of the radius and set them equal to each other and see if they match. So first, let's do that for the inner radius. So we have the torque at the inner radius is equal to mu times, and for the shear rate, we're just going to use the magnitude instead of the negative because we just want to show that they have the same magnitude. They don't need to have the same direction. And then we're going to multiply it by the area, which will be 2 pi Ri times h and times Ri. So the area here will be 2 pi Ri times h, because 2 pi r is the circumference of a circle, which will be the circumference of this inner cylinder times the height. And so a little bit of simplification here, we get 2 omega mu 4 pi h Ri squared 1 over k squared. So that is our function for the torque at the inner radius. So now we're going to do the same thing for the torque at the outer radius. So it's going to be very similar, except we're going to use the shear rate at the outer radius, and we're going to use the big R as the radius. So some more simplification gives us 4 times mu times omega k squared pi r squared h over 1 minus k squared. So if we're looking at these right now, we can tell that they're not actually the same. But we got to use this k term to be able to make these the same. So we're going to substitute in for r squared here, ri over k squared. And I'm just going to move that outside just to make it easier. See those k squareds cancel. And we're left with the torque at the outer radius is equal to 4 times viscosity times the angular frequency as pi as the height, the inner radius squared, all over 1 minus k squared. And you can see from here, the torque at the inner radius will have the exact same value as the torque at the outer radius.